Is it working better?
Yeah, that works. Thank you.
All right. Thank you for letting me know, actually, because I would have been just keep going without even knowing it. All right. Sorry. Technical issues. What I did was I paused the syncing with the OneDrive, and the OneDrive was all hung up, and that's why it's probably glitching. All right. So again, um, to pick up where we left off, since the force exerted by man is what we're looking for in part A, we had to basically go over um, all the forces in the x direction. So here I have three forces in the x direction, right? I have Fgx, I have Fa, and I have F friction in the x direction, right? And so sum of all forces equal to max. However, my acceleration is zero because it's kept from accelerating. And then sum of all forces in the x, three forces. Fgx, which is a direction of motion, that's why I'm going to keep that positive. Fa is in the opposite direction of motion, so it's negative. Friction is also in the opposite direction of motion, so it's negative. So when I set these two net forces equal to each other, 0 is equal to Fgx minus Fa minus F friction. So if I bring this negative Fa to the other side of the equal sign, I get positive Fa, and that is equal to Fgx minus friction. Well, what is FGX? Well, FGX is really nothing more than just opposite component of my FG of 30 degrees, right? So FGX is equal to FG times sine of theta, or mg times sine of theta. So m, 280, g, 9.8, sine of 30 comes out to 1372. But what about friction? Well, we know friction is equal to mu times F normal. But my F normal here has to be same as my FGY. Why? Well, let's figure it out. Since sum of all forces in the y direction is equal to MAY, and you know AY is zero because it's not levitating off the incline, or it's not going through the incline, right? And sum of all forces in the y direction is equal to, I have F normal, I'm going to consider that positive, right? Minus FGY, right? So since 0 is equal to F normal minus FGY, my FGY is equal to F normal. Right? All right? That's how we got to this, right? So F normal is equal to FGY. And since FGY is the adjacent component of my 30 degrees here, of my hypotenuse FG, my FGY is FG times cosine of 30 degrees. Right? And since FG is M times G, 280 times 9.8 times cosine of 30 degrees. And if you work that out, your F normal comes out to 2,376.4 newtons. So if you plug that in for your F normal and you multiply that by mu of zero point 0.4, you get your frictional force coming out to be 950.55 newtons. Okay? So now we have all the ingredients, right? We have all the ingredients to figure out what my force applied is. So if you work it out, you get Fgx, which is 1372, minus 950.55, and you get Fa is equal to 421.45 newtons as my force applied. All right. So once we have that, right? Once we have that, we can do part B now. Now, part B states the work done by the man on the piano. So we want to know how much work is done by the applied force, right? So if we were to draw these two vectors out, applied force is going up the incline, right? So here's the applied force. So force applied And delta x is actually going down the incline. So here's my delta x. So these two vectors are 180 degrees apart. So this theta is equal to 180 degrees. All right. So work done by applied force is equal to applied force dot delta x. So by definition of dot product is the magnitude of FA, which is 421.45, right? Times the magnitude of delta x, which is 4.3, times cosine of the angle between them, and that is 180 degrees. So if you work this thing out, you will get negative, because cosine of 180 is negative, 1812.2 joules. All right, and that's where we left off last Wednesday, and then we ran out of time, right? So now let's take a look at part C, right? Part C. What is part C? Part C asks, right? So the work done by man is done. Part C asks, work done by frictional force. So how much work is being done by the frictional force? So for part C, my frictional force is going to be acting up the incline. So here's my frictional force, right? And my delta x is acting down the incline. So here's my delta x. So my frictional force and delta x are 180 degrees apart from each other, right? So the angle between those two vectors are 180 degrees. So work done by friction is equal to frictional force dot delta x, right? So what is work done by friction? Well, work done by friction then is equal to frictional force, right, which is 950.55, right, times delta x, which is 4.3, times the cosine of the angle between F friction and delta x, which is 180 degrees. That's straight by definition, right? Dot product definition. Therefore, if you work that out, my frictional force is doing negative 4,087.4 joules of work. Okay? All right. What about part D? Part D asks, how much work is done by force of gravity? How much work is done by force of gravity? So for part D, I want to know how much force of gravity is doing the work. So here's my Fg, and here's my delta x. So what is the angle between Fg and delta x? Come on, somebody say it. What is this angle? Which is this angle right here. All right. 60 degrees is correct. All right. Thank you, Ishan. Appreciate it. Right? 60 degrees is correct. So if we were to find work done by Fg, right? So work done by gravity is equal to Fg dot delta x. Right? So that comes out to Fg. What is Fg? That is mg, right? So if you were to do mass times acceleration due to gravity, that's 280 times 9.8, right? So what is Fg equal to? That's 280 times 9.8 times delta x, which is 4.3, times cosine of 60 degrees. That's how much work is being done by force of gravity. All right? So I guess if you work this out, so work done by force of gravity comes out to, I get 5,899.6 joules. All right. All right. What about part E? Part E asks, what is the net work done on the piano? Well, for part E, work net is equal to the net force dot delta x. But what is my net force? My net force, if you look at it here, is equal to 0 because acceleration is 0. So my work net is equal to 0 times 4.3, right? So my work net is equal to OJ. No, all right. Or if you want to figure out another way to find net work, so work net can also equal to, or, right, work net is equal to, you could say work done by 4 forces, right? Well, we could find how much work is done by F normal. How much work is being done by F normal? Well, since F normal and delta x are perpendicular to one another, we know cosine of 90 is 0. So work done by F normal is equal to 0. So maybe we could even say that, right? So work done by F normal is equal to 0. So if we add up all the works done by all the forces, so we have 4 forces doing work, right? Some are going to go to 0, some are going to be non-zero. So here we got work done by the applied force plus, right, work done by friction, right, plus work done by, what else? Work done by gravity, plus work done by F normal, which is 0. So if we add up all the works done by all the 4 forces that we have 1, 2, 3, 4 forces. So work done by all 4 forces. What do we get? We get work done by applied force came out to negative 1812.2. Right? Work done by friction is negative 4087.4. Work done by gravity, we got plus 589 99.6 plus 0. And if we add all these up, guess what we get? My work net comes out to same OJ. All right. So it's important to realize the work done by the normal force here is 0 because the cosine of 90 is 0. Okay. All right. I hope that explains this problem. I will give you a quiz on this. Right? I will give you a quiz on a dot product and this problem right here. Right? Should be pretty easy. Okay. Dot product, you should already have an example problem of that already. All right, good. Let's take a look at next. All right, lesson 2. Work and kinetic energy theorem. So we were talking about how we put work and energy as putting the kinematics and dynamics together, right? So first thing we learned about was kinematics, which is how things move and how things are, like the behavior of motion itself, right? Then we never really talked about what caused that motion, but it is a dynamics part that we learned that any push or pull can cause objects to accelerate and make it move, right? So when you do any kind of a push to an object and you make it move, you're doing some work on it. And that's what we talked about in lesson 1. Well, that work, when you make it move, you're giving it kinetic energy, which is energy of motion, right? Well, let's see how they are related together with work and kinetic energy, all right? So first, if we were to take a look at our Newton's second law, F equals ma, right? Then, remember this equation number 3, Vf squared is equal to Vi squared plus 2a delta x, right? Well, let's put the F in here then. Fine. If we make this f of x move this object at certain distance, delta x, right, we're going to actually change its speed, right? Because if you're pushing on it, you're going to accelerate it, and when you accelerate it, you're going to change the velocity, right? So if we were to, okay, use this, solve for x, or delta x, right? Then we have is, right, we have Vf squared minus Vi squared over 2a is my delta x. Okay, I hope that you guys can see that. Because if I subtract this to the other side, I get negative Vi. Then divide that by 2ax. Now, I will substitute this into my second equation, right here, which is work net is equal to F dot delta x, which is same as Fx times delta x times cosine of 0 degrees, which is, this goes to 1, right? And that's how we get Fx delta x. So if we plug in this value into here and finish that off with f of x being ma, right? So here, work net now is equal to, right? F of x is max. Delta x is vf squared minus vi squared over 2ax. Look what happens to my ax. My ax cancels out, giving me, right, mvf squared minus mvi squared, whole thing over 2. I can distribute this 2 out to both of these, right, and say 1/2 mv final squared minus 1/2 mv initial squared. This is what my work net becomes. This is known as the work kinetic energy theorem. So if I take a look at just this term right here, or just this term right here, this term, 1/2 mv squared, is known as the kinetic energy. Right? The kinetic energy is equal to 1/2 mv squared. Does that look familiar? Right? Like if you take the half away, E is equal to mc squared, right? Yeah, interesting, huh? Well, guess what? Can this kinetic energy ever be negative? Well, let's take a look. 1/2. 1/2 cannot be negative. It's just 1/2. You're not going to have negative mass, right? Unless you're working with antimatter, but I don't think you're going to have antimatter in Newtonian physics. So mass can never be negative. When you square the v, it doesn't matter anymore, right? When you square the v, your v will always become positive. When your v squared becomes positive, then positive times positive times positive will always be positive value. However, change in kinetic energy can be negative, right? Because you have final kinetic energy minus the initial kinetic energy. The change in kinetic energy can be negative, but kinetic energy by itself can never be negative. Okay? That's very important. And it is a scalar quantity, which means it does not have any direction. So kinetic energy does not have direction. So it doesn't matter which way it goes, or which direction it goes. Kinetic energy is just a scalar quantity and is not a vector, so it does not have direction. Okay? So if I were to consider this 1/2 mv final squared to be my final kinetic energy, right, and 1/2 mv initial squared to be my initial kinetic energy, right? So my kinetic energy final minus the kinetic energy initial. That just becomes change in kinetic energy, right? Delta kappa epsilon. Right? Sounds like a Greek fraternity, right? So work done, the net work done, is equal to change in kinetic energy, or 1/2 mvf squared minus 1/2 mv initial squared. Very, very important. So we will use this to solve some problems. Okay? All right. So, to solve problem by applying this, since we know work done is equal to F dot delta x, this F dot delta x must equal to 1/2 mvf squared minus 1/2 mv initial squared, right? So we know how to find work. Now we know how to find kinetic energy, so we should be able to figure out any of these things if they're asked. All right, so here, an example problem states a 3 kilogram ball is thrown at a wall, with initial velocity is equal to 5 meters per second positive x hat, right? So here we have a ball is thrown to a wall, right? With the initial velocity of positive 5 meters per second x hat. And this ball mass is equal to 3 kilograms. That's a pretty heavy ball. Then the ball rebounds. So this is the initial condition. The final condition is the ball rebounds, right? So my VF is equal to negative 4.2 meters per second x hat. The mass will not change, right? Mass is not lost. So it's going in at 5, but it's coming out at 4.2. Right? So calculate the change in kinetic energy of the particle. Well, change in kinetic energy is equal to kinetic energy final minus the kinetic energy initial. We know kinetic energy is 1/2 mv squared. But since we're looking for the final kinetic energy, we use 1/2 mv final squared minus 1/2 mv initial squared. That's my change in kinetic energy. So 1/2 times 3 times my VF is negative 4.2, but we have to square that. That will become positive. Minus 1/2 times 3 times 5 squared. So let's work it out. What do we get? So here I have 0.5 times 3 times 4.2 squared. Now notice I did not put negative 4.2 because when I square it, I'm going to get positive anyway, so it doesn't matter, right? So I get 26.46 joules for my final minus 0.5 times 3 times 5 squared. And that I get 37.5. So what is my change in kinetic energy? So my change in kinetic energy becomes, right, 11.04 joules. So what does that mean? That means my work done is also equal to negative 11.04 joules. This means this is how much energy is lost. Now, when we say the energy is lost, we don't mean it's like gone, like just poof, disappears. It just means the energy is transferred to something else other than the kinetic energy. So we did not have kinetic energy coming back exactly the same amount that we put in. And usually this energy lost, the negative joules, pretty much converted into heat. Okay, so either heat energy, sound energy, etc., etc. Okay, so it's not lost, but it's just turned into heat and it dissipates throughout the universe. It's not put back into the system. Yes.
What type of energy were you talking about?
What's up? I'm teaching.
Sound energy? What is sound energy,
That's
Mr.
Dr.
Kim?
Giuseppe bothering me again. All right, that's Dr. Giuseppe. Sound energy. He was demonstrating sound energy. Anyway, so that's how much energy was pretty much lost as the ball hits the wall, right? And rebounds. So what about part B? If the final velocity of the ball comes out to be now negative 5 meters per second, I said. So what happens then? Well, obviously, in that case, no energy is lost. That means we should have zero for the change in kinetic energy, right? Well, let's see if that's true, right? So change in kinetic energy is kinetic energy final minus the kinetic energy initial. So 1/2 mv final squared minus 1/2 mv initial squared, which is 1/2 times 3 times vf happens to be negative 5 squared minus 1/2 times 3 times 5 squared. We know when we square the negative 5 becomes positive, and this becomes 37.5 minus, we already know this is 37.5, and guess what? We have no energy lost whatsoever. So there is no change in kinetic energy. Voila. All right. All righty. So now that I showed you how to do this, we're going to go out into the breakout session and see if we can do the next 2 pages with group work, okay? And then we'll come back in, I guess, 25 minutes, all right? 25 minutes. And then we'll go over this, all right? So let's see if you can suffer through this on your own, all right? Now here, kinetic energy is also temperature, right? And if you took chemistry already, right? Thermal energy comes from how much energy an air molecule possesses, right? The kinetic energy the air molecule possesses, and that pretty much is the same thing. So we can actually figure out how fast those oxygen molecules are moving using the kinetic energy theorem, right? All right, this one, just use variables, okay? Just use variables. And these pretty much, okay, are plug-in chugs, okay? So this use work kinetic energy theorem. This one, I'm going to give you a hint. Your work done is by friction. So set your work friction is equal to change in kinetic energy. All right? All right. So let's see if you can work on this in a breakout session. All right. I'm gonna so I'll make it 5, 6. I'll make it 6. All right. I'll pause the video. And now we're back. So at room temperature, an oxygen molecule with mass of that many kilograms typically has kinetic energy of about this many joules. How fast is it moving? So since we know kinetic energy is equal to 1/2 mv squared, right? We're looking for v, right? So here, this itself is kinetic energy, right? So 6.21 times 10 to the negative 21st is equal to 1/2 times 5.31 times 10 to the negative 26 times v squared. So v is equal to square root of, right, 2 times 6.21 times 10 to the negative 21st over 5.31 times 10 to the negative 26th, right? So let's see what we get when we work this thing out. So we get 2 times, right, 6.21 EE negative 21st power, right? And then you divide that by 5.31 EE, right? Negative 26 power. And then you have to square root that sucker. Boom. So you get about V is equal to 483.6 meters per second, right? That is definitely more than speed of sound. That's about 1.5 speed of sound, so that's why you don't hear it, okay? Because if you were to able to hear that thing, it would drive you nuts. All right, next. Here we have kinetic energy of an arrow is doubled. By what factor has the speed increased? All right. So we know the kinetic energy itself is 1/2 mv squared. So if we double that, if you have twice the kinetic energy, right, that is equal to 1/2 mv, I guess, prime squared. This prime is not a derivative. It's just a new v, right? The new v. When we double this kinetic energy, right? So 2 times 1/2 mv, I'll say mv naught squared is equal to, right, 1/2 mv prime squared. So notice how 1/2 m's can cancel out. So we have 2v naught squared is equal to v prime squared. And if we square root both sides, what we get is v prime is equal to now radical 2 times v naught. So it has increased the speed of radical 2, right, v naught. And what is radical 2, right? That's 1.414, so v prime is equal to 1.41 v naught. So if you double the energy, you're only going to get square root of 2 much of speed increase, okay? So what happens if you double the speed, right? So let's say we have kinetic energy, right, naught is equal to 1/2 mv naught squared, let's say, right? The new kinetic energy prime is equal to, right, 1/2 times m, right, 2v naught quantity squared. So we double the speed basically. So when we double the speed, what happens? We have kinetic energy prime now is equal to 1/2 m times, when we square the whole thing inside this parenthesis, we basically get 4 v naught squared, right? That is 4 times 1/2 m v naught squared, right? So the kinetic energy prime is 4 times the original kinetic energy required. So if you want to go twice as speed as original speed, so let's say you're spending so much energy for going 55 miles per hour, but if you're going 110 miles per hour, you have to spend 4 times as much energy to double the speed. So you'll be wasting 4 times as much gas going twice the speed of whatever speed that you were going, okay? So I don't know. I guess you have to compromise, right? You have to compromise. All right. Next. Um, how much work is required to stop an electron which is moving with speed of this much? Well, work is equal to change in kinetic energy, right? Which is equal to kinetic energy final minus the kinetic energy initial. Well, how much work is required to bring this much mass moving at this speed at rest? So here, my V final is 0. So 1/2 mv final squared minus 1/2 mv initial squared. My V final is 0, so this whole term drops out. So the work is equal to 0 minus 1/2 times 9.11 times 10 to the negative 31st times 1.90 times 10 to the 6 squared, right? So let's work it out. So 0.5 times 9.11 EE negative 31st times, right, 1.9 EE 6th squared, right? So what do we get? We get 1.64 times 10 to the negative 18th joules, and it's negative, right? 1.64 times 10 to the negative 18th joules of work is required to stop that electron. That's very small. I mean, you don't really need that much. Okay? Now for number 10. At an accident scene on a road, on a level road, investigators measure a car skid mark to be 88 meters long. Wow, that's a long skid mark, right? That's almost the whole football field. It was a rainy day, and the coefficient of friction was estimated to be 0.42. Okay. Use these data to determine the speed of the car when the driver slammed on and locked the brakes. Right? Why does car's mass not matter? Well, what's really stopping the car? So here, okay, the car, the skid mark is going this way, right? So that's the delta x, right? So the skid mark is 88 meters long. So delta x is 88 meters long. We ran out of time. Sorry. All right, we'll continue this, I guess, next time, Tuesday. All right. Have a nice day. All right. See if you can finish this up if you didn't finish up. All right.
Thank you.
Have-
Thank you.